Hello everyone, in this video we are going to discuss about classification of cross section of beams.
So the concept is classification of section. So as we discussed, classification of section is nothing but we are going to use one type of cross section, mostly I section, no doubt. So that I section is going to be classified based on some criteria. So what is that we are going to see now? Based on yield moment, plastic moment. So we represent yield moment with my. Had we discussed about this or not? So where we have discussed about this yield moment? In the beginning class in plastic analysis, we have discussed about this yield moment. Okay. So in the beginning introduction of the plastic analysis itself, we have made it clear what is plastic moment and how to calculate it. Next, yield moment. So what is yield moment and how to calculate it? Of course, we have discussed about plastic moment also in the same topic, that is in plastic analysis. Plastic moment. MP. So if you remember or if you once recollect the formula for yield moment my, how to calculate my? That Fy into Z. Agree or not? So how to calculate that MP? MP is equal to Fy into Zp. So strictly speaking, we have to call it as Ze. So Ze is nothing but elastic section modulus. Elastic section modulus. So formula for it is I, moment of inertia, by Y, maximum distance from the neutral axis, that is elastic section modulus. Now coming to Zp, what is Zp? Zp is plastic section modulus. Okay, plastic section modulus. And whose formula is A by 2 into Y1 plus Y2. So I guess about this formula you are discussed in strength of materials, and about this formula we are discussed in our session itself. Okay, in this discussion of design of steel structure itself, in the beginning topic of it, that is in plastic analysis, we have discussed about this Zp and this yield moment and plastic moment in detail, how the cross section is transforming from yield state to plastic state. So the moment of resistance of a particular cross section at yield state is known as yield moment, and at plastic state is known as plastic moment. And we know how the cross section is going to the plastic state and what is happening at this state. So at that state we have discussed it in and out, or in detail we have discussed about this. So now the classification of this section based on this yield moment and plastic moment, and this classification is also based on one more criteria, that is width to thickness ratio. So that is width to thickness. So width we represent with B and thickness TF. It means outside, so I'll explain the diagram. So width to thickness ratio and or comma depth to thickness ratio. It means D by TW. So I'll explain in the diagram what is D, what is TW, what is B and what is DF, everything. But here you should understand that the classification of section mainly based on yield moment, plastic moment. So this is one classification. The classification is same, but based on the yield moment and plastic moment. And again that classification is based on width to thickness ratio and depth to thickness ratio. So based on these criteria, we are going to classify sections. Okay, so yield moment and plastic moment and width to thickness ratio and depth to thickness ratio, I am going to show it in the diagram. So take a one standard rolled steel section. Okay, standard rolled steel section. That is obviously I section. Okay, this is an I section. Okay, so this is an I section. We know that overall depth of the I section is from top to bottom fiber. So here I am going to represent that with H. Of course, we are represented with capital D, but here I'm going to represent with H. And the depth of the web. So only I'm considering the depth of the web. That I'm going to represent with D. Clear? And this is the width of the flange, which is B suffix F, BF. And now B, what is B? So B is the outstand width. So this is from the off. So this is B. So what is B here? B is the outstand width. B is the outstand width. So from this we can say B is equal to half of the width of the flange, means BF by 2. Agree? And what is meant by TW and TF? So TW is the thickness of the web. This is. And TF is the thickness of the flange, TF. So those are the dimensions. So based on these dimensions and based on their moment carrying capacity, that is yield moment and plastic moment, now the beam sections are classified. So what is the classification? Let us see. So now so far we have discussed the criteria for the classification. Now let us see what is that classification. So take this diagram. So represent the diagram very clearly. So whenever you are taking this in your notes, so take this very clearly. So if the diagram is clear, so upon revising, so whenever you are revising the things or concepts, then it will be very clear to you. Okay. So I'll explain what are those classifications. So I'm going to rub this everything. So first classification is, so we are going to classify beam section as a plastic section. Plastic section. So first I'll give you the definition, later I'll explain on the curve. So when a particular cross section is called as a plastic section, let us see. A section which can develop plastic moment carrying capacity, plastic moment MP, okay, which can develop plastic moment and forms sufficient number of plastic hinges to fail in plastic mechanism. Is called as plastic section. So if you go through the definition, once again I repeat, a section which can develop plastic moment, MP, and forms, so not for, and forms sufficient number of plastic hinges to fail in plastic mechanism is called as plastic section. It means if you once remember or if you once recollect the concept of plastic analysis, so there whatever the beam we have discussed, okay, all the beam sections what we have discussed in plastic analysis fails by this or not? Fails by this case. It means first they develop plastic moment carrying capacity and then they forms the sufficient number of plastic hinges and ultimately they fail by forming mechanism. Agree or not? So now the sections what we are going to design in plastic analysis are the sections what we are going to use in plastic analysis are known as plastic sections, simply to say. Okay, it means, so of course the same form of definition we have not discussed in plastic analysis, but the sections what we are going to use in plastic analysis are what we are going to design in plastic analysis are known as plastic sections, simply. Clear? This is the first classification. Second, compact section. Second is compact section. Now let us see the definition. A section which can develop plastic moment MP, but cannot form sufficient number of plastic hinges, to fail in plastic mechanism. Fail in plastic mechanism before buckling. This is compact section. So now, what is the definition of compact section? So for example, for a section, I section to be classified as a compact section, it can develop plastic moment carrying capacity or MP, but it cannot fail by mechanism. It means to fail in mechanism, it requires n+1 plastic hinges. Yes or no? It means sufficient number of plastic hinges are required. But here for compact section, it is not going to fail by forming mechanism. It fails by buckling. So before buckling, it forms sufficient. Okay, it cannot form sufficient number of plastic hinges. So simply it fails by buckling. So the difference between compact section and plastic section and compact section is that similarities, both can form plastic moment carrying capacity, but plastic section fails by plastic mechanism, it fails by buckling. So it cannot form sufficient number of plastic hinges. That is the difference. Next, third, semi-compact section. Okay, the extreme fibers of the cross section of a section, the extreme fibers of section in compression reaches to yield state, and cannot develop plastic moment before local buckling. So now if you see the semi-compact section, so this section, you can say this section can develop only yield moment. That's it. So if it develop yield moment, it buckles or it fails. So it even can't develop plastic moment also. That is a semi-compact section. So this is a 3, and one more is there, that is a slender section. So I'm going to rub this. So take the definitions. I'm going to rub this and I'm going to write the definition of slender section. So simply to say, plastic section is nothing but which can develop MP and fails by plastic mechanism, and and compact section is nothing but which can develop MP and fails by buckling. It not fails by mechanism, but here it fails simply by buckling, and it cannot develop even MP also. It can develop only MY, yield moment only. That is a semi-compact section. Now the last classification is slender section. The fourth classification. A section which cannot develop yield moment also, but fails in local buckling. So this is the definition of slender section. So a section which cannot develop yield moment also. So it cannot develop even yield moment My also, but it fails in local buckling. Agree, this is a slender section. So now these are the classifications of a beam section. What are those classifications? Plastic section, and then compact section, and then semi-compact section, and then slender section. So these are the classifications. So this classification is based on now yield moment and plastic moment. So now I'm going to explain this with a curve or graph. So for this graph, on x-axis I'm going to take the moment m, and on y-axis I'm going to take the curvature. So here is my and here is mp. Okay. So if you observe here, for a slender section, the graph will be like this. It means the stress level. If you see the stress diagram for a slender section, this is a stress diagram. So at extreme fibers, the maximum will be there, which is less than F. So F will be the stress at the extreme fiber. So at this extreme fiber, the stress is Fy. So extreme fiber stress is Fy, which is less than Fy, means yield stress. So this is the graph for slender section. So this is for slender section. Next, semi-compact section. So we know that semi-compact section can develop yield stress or yield moment. So like this. Okay, so this is a semi-compact section. So now if we see the stress curve, the stress curve here is like this. So here it is Fy. So this is for a semi-compact section. So it means it can develop yield moment, okay, but fails by buckling, and it cannot develop plastic moment carrying capacity. So this is semi-compact section. Now next is compact section, like. So it can develop plastic moment carrying capacity, but it fails by buckling. So it not fails by mechanism. So for that, if we see the stress distribution, so we know that how the stress distribution in plastic state, the same stress distribution for compact section. So when it can develop the plastic moment, if it reaches to the plastic state, then only it can develop the plastic moment. Agree or not? So here it is Fy, and also here also it is Fy. Agree? So this is compact section. Now next is plastic section. So we know that plastic section can develop plastic moment carrying capacity, and it fails by rotation. It means it fails by forming the mechanism. It means it rotates. So infinite rotation will take place. So that rotation is going to represent on the curve line. So this is plastic section. So it means you can say the infinite rotation. After that it fails. But here, just if you take compact section, just after attaining or developing the plastic moment, it fails. Here, just after attaining yield state, it fails. That is semi-compact. But a slender section, before attaining yield stress or yield moment, it fails. That is the meaning. So this is plastic section. So for both compact section and plastic section, the stress distribution is same. This is the stress distribution. For compact section and plastic section, stress distribution is same. So this is the stress distribution for compact section, and this is the stress distribution for slender section. So now this the classification of plastic section, compact section, semi-compact section, and slender section are based on the plastic moment and yield moment. Clear? So this is one classification. So this is one criteria. Now let us see the other criteria, that is based on the dimensions. Okay, let us see based on the dimensions. Now here the classification is based on width to the thickness and depth to the thickness. B by TF. If this B by TF is 9.4 epsilon, then that cross section is known as plastic. So if the width to the means that width of the outstand to the thickness of the flange is 9.4 epsilon. So epsilon is nothing but so here I will write. So epsilon is nothing but under root 250 by Fy yield stress. For mild steel we know that Fy is 1. Agree or not? So for mild steel or for Fe 410 grade, Fy is equal to 250. So you can take epsilon is equal to 1. So as we discussed in the introduction itself, in our structural steel mostly we are going to use mild steel, but there are some cases where we are not going to use mild steel. So simply epsilon is nothing but under root 250 by Fy. Okay, yield stress for mild steel it is 250, so it comes out to be 1, but not in all the cases. So now if that ratio that outstand to the thickness of the flange is 9.4 epsilon, then it is plastic section. If it is 10.5 epsilon, then it is a compact section. If it is 15.7, it is semi-compact section. That is the ratio of B by TF. Next, D by TW, that is depth of the web to the thickness of the web. So if it is 84 epsilon, so for mild steel simply 84. So if this ratio is 84, then it is plastic section. If this ratio is 105 epsilon, then it is compact section. If it is 126, then it is semi-compact. So these are the ratios. So given by the code book IS 800 2007. Take the values. So I'm going to run this. Now coming to the slender ratio, slender section. So actually we know that all the steel members, structural steel members are manufactured, okay, are manufactured in the various industries like steel plants or Steel Authority of India SAIL. So but we know that not in all the cases we are going to use those rolled steel sections. It means we have discussed in columns that if we take column, so if the cross section of the column is not sufficient, means if the cross section or required section to take the load P as a column is not sufficient, it means in the steel table no section is available to provide that required area. It's not sufficient, then what to do? We have to make a built up section or not, means we have to take two channels or two angles or two I sections and we have to make a connection. It means those are called as built up sections. Okay, those are called as built up sections, and which are manufactured in the industries is called as rolled steel sections. So if the rolled steel section is not serving our purpose, then we go for built up sections. That is quite obvious. Now whatever the ratios we have discussed is for rolled steel sections. Okay, is for rolled steel section. So it means usually we manufacture beam or I section either as a plastic section, means if you follow that B by TF as a 9.4, okay, by following that specification, if we design or if we manufacture, then that is plastic section. If we follow that B by TF as a 10.5 and we manufacture, then it is compact section. If we follow D by TW as a 84 epsilon, then it is plastic section. So if we follow those ratios and manufacture, then obviously the sections will be plastic, compact and semi-compact. But usually slender section is a plate girder, which is a built-up section. So that we are going to discuss in the plate girders. Okay, design of plate girders I'm going to explain. So generally rolled steel sections are never slender. Okay, rolled steel sections are never slender. Rolled steel section mostly plastic or compact, in some cases semi-compact. Usually they are plastic and compact, in some cases semi-compact. So we can take that rolled steel section may be plastic, compact and semi-compact. They never slender. That is the reason there exists no ratio for slender section. The either B by TF or D by TW. Clear? That is why the ratio is not given for the slender section. So slender section is only built up section. So whenever we are going to build a section, then only that section can be classified as slender. So best example of a slender section is plate gutter. So we are going to design plate gutter as a slender section. So remaining, wherever we are going to use beam, so all those beams we are going to design mostly as a plastic section. In some cases a compact and semi-compact, depends. Clear? That is the thing.